The rate of reaction between magnesium ribbon and dilute hydrochloric acid at room temperature is investigated. The apparatus is shown in figure 11. The volume of hydrogen gas given off was measured at regular intervals during this reaction. So we've got dilute hydrochloric acid, magnesium ribbon, and we got the upside down inverted measuring cylinder to collect bubbles which displace the water inside the cylinder, and it pushes the water level down so you can measure how much gas is being collected at certain time intervals to get an idea of rate of reaction. What we mean is how the rate at which product is formed, in this case a gas. The graph in figure 12 shows the results of this experiment. State a change that can be made to the apparatus in figure 11 to measure the volume of gas more accurately. This is basically an inferior version of collecting gas compared to the gas syringe method, which is far more accurate, because it just basically, you don't need to faff around with water. This just pushes this plunger back, and every 10 seconds or 30 seconds or whatever interval you choose, you can measure how much gas is being produced. So a gas syringe is always a better solution. Unfortunately, they're quite expensive, so we don't use them in class labs very often, although we can demo it sometimes. So use a gas syringe. A tangent has been drawn to the line on the graph in figure 12. Calculate the rate of reaction at this point. So calculating a rate of reaction can be very easy if you've got a straight line, because you just divide the rise by the fall. But when you've got a curved line, as you often do, you have to use a tangent to produce a sort of simulated a straight line at that point. And once you've got that straight line, you're just trying to find 2 points where you get a nice, tidy, clean bisection of the corner of a square, so you can get a nice read off the graph. So I've picked my 2 points here and here, though you could pick them elsewhere, wherever you find a position. But I picked it here because it cuts through the corner of this square and the corner of this square nice and neatly. Now, once I've done that, I've got to basically read off the values of this graph. To work out the rate of reaction, you do the amount of product, which is this y-axis, by the time it took, this x-axis. So y divided by x, or amount of volume of product divided by time it took. So over here, we can see we've got to work out the value of each square. So if we got a rise of 20 here, so increase of 20, and we've got 5 squares, which is divided across 5 squares, do 20 divided by 5, so you know each square is worth 4. So here, 4, 8, 12, 16, 20, so this is 20 across. Here it's much simpler, it's 2, 4, 6, 8, 10, so 10 here. So we do 10 divided by 20, and that will give us the rate of reaction, rise divided by the horizontal. So 10 divided by 20 is 0.5, and it's given you the units in centimetre cubed per second. On the graph in figure 12, draw the line you would expect to obtain if the magnesium ribbon in this experiment was replaced with an equal mass of powdered magnesium, all other conditions kept the same. Alright, so to draw this line, what you've got to remember, I'll show you a few examples here just in case it comes back to you in another way. Basically, if you increase the surface area or increase the temperature or add a catalyst, what you're doing is increasing the rate of reaction. You still get the same amount of product formed at the end, but the time at which you reach that end point is sooner. So in other words, you'll get a left shifted curve showing that you've reached that end point sooner. You can see where we got to that point there at this time here, rather than at this time here. So this is showing a faster rate of reaction. Now you just have to sketch your version of this. It doesn't have to be exactly the same as mine. It could be here, it could be there, but the point is it's left shifted. Now, if it was, however, something like concentration, then you've got to be careful, because if you increase the concentration, it does also increase the rate of reaction. But now, because you're also adding more chemicals, you increase the amount of product formed. So concentration is the only one where it increases the rate of reaction, but you also raise the product line because you get more product produced. Now, the question was about surface area, but I just thought I'd bring that in now in case it comes back to you next year, like with concentration instead of surface area. So surface area would be this here. And just to add, if they reduce the surface area, it would just be similar, but it'd be right shifted. It would take longer to get to the same point like this. And same with lowering temperature, removing a catalyst, and reducing the concentration. That means you'd have less reactants, so it'd end up like this. The balanced equation for this reaction is Mg plus 2HCl produces MgCl2 plus H2, magnesium plus hydrochloric acid is magnesium chloride and hydrogen. In another experiment, 0.1 moles of hydrochloric acid, HCl, were reacted with 0.1 grams of magnesium ribbon. Calculate the number of moles of magnesium, Mg, in the 0.1 gram sample of magnesium ribbon. The relative atomic mass of magnesium is 24. So this is quite easy. You're just trying to work out the number of moles. So just remember this equation. This is probably the most important equation you take in with you to the chemistry exam. There's not many to learn, but this one is really critical. You will not do as well without learning this equation. That's a guarantee. So learn it. So number of moles is mass divided by AR. So you just do mass, which is 0.1 grams, divided by AR, which is 24, which gives you that 0.0042 or 4.2 times 10 to the minus 3. Because if you want to write it in standard form, this shifts this way 3 spaces, 4.2, but obviously minus 3 signifies that the reality is this decimal point would be moved back 3 places. In a further experiment, 0.5 moles of hydrochloric acid, HCl, were mixed with 0.5 moles of magnesium, Mg. Use the equation to show that in this experiment the magnesium is in excess. So this is about limiting reactant. So a limiting reactant is the one that's used up, and the one in excess means there's plenty remaining, or there's stuff remaining after the reaction's finished. So to do this, we have to refer back to the chemical equations. What we're saying in this chemical equation is 1 mole of magnesium reacts with 2 moles of hydrochloric acid to get this. Now, if we only have 0.5 moles of hydrochloric acid, so not 2 but 0.5, and 0.5 moles of magnesium, we basically have less hydrochloric acid than is needed. In other words, because normally this reacts in a ratio of 2 hydrochloric acid to 1 magnesium, we now have 1 to 1 over here. So hydrochloric acid has become the limiting reactant because we needed 2, but this is a ratio of 1 to 1, or 0.5 to 0.5, which is the same as 1 to 1, and therefore we'd assume that magnesium would be in excess. So how do you write this? The equation shows you need to react 2 HCl with 1 Mg. That's how we know that 2 moles of HCl with 1 mole of magnesium. That's how we know that magnesium is in excess. Okay, the essay question. 2 substances A and B each form a colourless solution. If the solutions are mixed in a beaker, A and B react to form a coloured product. The rate of reaction between A and B can be investigated by placing the beaker containing the mixture on a cross on a piece of paper and timing how long it takes for enough coloured product to be produced to make the cross invisible when viewed from above through a solution. So this is a technique you might have tried in a school lab. So you basically have a beaker resting on a, let's say, a little piece of paper like this, and the piece of paper has a cross on it like this, and as the coloured solution basically forms, as the reaction continues and gets darker and darker, the cross gets obscured, and then you stop the clock when you can no longer see the cross. It's not the most accurate method because it's qualitative. You're using your eyes rather than an instrument to measure. Use the results of these experiments to explain in terms of the behaviour of the particles, the effect of changing temperature, and the effect of changing the concentration of A in solution on the rate of this reaction. So firstly, let's just have a look at it. We can see the concentration of A in solution. So in experiment 1 it's 10, experiment 2 it's 10, but in experiment 3 we've increased the concentration. In experiment, what we're doing here is temperature's lower here but higher in these two, and the time for cross to become invisible. So you can see here that when the temperature is increased here, we massively reduce the time of reaction, so it's a faster reaction time. And when the concentration is increased here, we also increase the reaction time. Reduce the reaction time, so it's a much faster rate of reaction. So let's have a look at this process as an overview before we start answering the question. So there are bonds between molecules holding them together, and before new molecules form, you need to break these bonds so new bonds can form to make the product. So you can see here they've bonded in different ways. Now for this to happen, 2 things must occur. You must raise the energy, or the energy in the kinetic store of these particles, so they move faster, because if they move faster, when they collide, they will do so successfully. That means they'll collide with enough force to break the existing bonds, allowing new bonds to form. So the amount of energy you need to raise in terms of their kinetic store to make this happen is called the activation energy. So chemical reactions occur based on successful collisions, or the frequency of successful collisions will affect the rate of chemical reactions. So how often these chemicals collide affects the rate of reaction. So any factor that affects the frequency at which these molecules smack together and basically form new bonds will increase the rate of reaction. Now, firstly, temperature does this, because if you increase the temperature, you increase the amount of energy in their kinetic store, so they move faster, which increases the likelihood or the frequency of successful collisions. The other thing is, if you increase the concentration, what we're saying is there's just more particles in the same area, in the same space, three-dimensional space. So there's a greater chance that they'll knock into each other, increasing the frequency of successful collisions. So both temperature and concentration, if you increase them, you will get a faster rate of reaction. With concentration, you'll also make more product because you have more reacting molecules in there. So you can see that both of these things, if this was the lower temperature and lower concentration, adding more concentration or increasing the temperature will increase the rate of reaction. So in the same amount of time, more product is formed. So here only that much product, but with more temperature, that much product. And you'll get to the end point faster. Here we've reached the end point, whereas here we've reached the end point in the original reaction. So use the results of the experiments to explain, in terms of the behaviour of particles, the effect of changing temperature and the effect of changing concentration. So firstly, we have to start by explaining the basis of chemical reactions. So particle collisions occur when there is sufficient energy. So when there's enough energy, particles will collide. Rates of reaction increase when particle energy increases and the frequency of collisions increase. So that's the basis of a chemical reaction, frequency of collisions due to particles having enough energy. So if you express that in a fairly clear way, you'll address the first part of the question. Now let's look at temperature. So with temperature, experiment 2 carried out at a higher temperature than 1. So if I just put this here, experiment 2 was carried out at a higher temperature than 1. So particles have more energy in their kinetic store. So they move faster, leading to more frequent collisions between particles in solution A and B. Collisions will have more energy, so will have minimum activation energy when they collide, leading to a higher frequency of successful collisions. So what that means is they've already reached their activation energy. You don't need to add much more energy to get the reaction going. They already have the necessary energy, so it'll collide and the reaction will occur much quicker. With concentration, experiment 3 carried out at a higher concentration, so more reacting particles in the same volume of reaction mixture, so a greater frequency of successful collisions between particles in solution A and B. Remember, you do not have to write all of this to get 6 marks. This is just covering absolutely everything that you need to know, but you could not. There's certain bits you could edit out and still get 6 marks, so always give it a go and address every part of the question.